All right, welcome. Today, we are going to tear down and rebuild one of the most important tools in modern AI, the convolutional neural network, or CNN. If you're doing anything with computer vision, you know this is the absolute workhorse. We're going to see how it's built from the ground up.
So here's our roadmap for today. First, we're going to dig into why a regular old-school neural network just completely falls apart when you show it a picture. Then we'll start building our CNN piece by piece, starting with the convolutional layer, that's where the real magic happens, and the super efficient pooling layer. After that, we'll see how we take all those features we found and turn them into an actual prediction. And finally, we'll look at how the pros optimize these things to get truly incredible results.
Okay, first things first, the core problem. We have these really powerful models called artificial neural networks, or ANNs. So why can't we just show one an image and call it a day? Well, it turns out there's a simple but really fatal flaw in how they're designed to see the world. To get a 2D image into a standard ANN, you have to do something kind of brutal. You have to flatten it. You literally take that beautiful grid of pixels and just unroll it into one long, single-file line of numbers. And in that one move, you've completely destroyed the most important piece of information in the image, the fact that pixels have neighbors. All that spatial structure, gone. And here's what that really means in practice. You know, if you move a cat from the left side of the picture to the right, to us, it's the same cat. But to a flattened ANN, it's a totally different input vector. It's completely confused. It loses the whole idea of shapes and objects. But the other massive headache, from an engineering perspective, is the parameter explosion. If you connect every single pixel to the network, you end up with a model that is just astronomically huge, impossibly slow, and a nightmare to train. So this brings us to the elegant solution, and it starts with the absolute heart of a CNN, the convolutional layer. This is where all the smart feature detection really happens. And at the center of this layer is a little thing called a kernel, or filter. You can think of it like a tiny magnifying glass that's trained to spot just one specific thing, maybe a vertical line, a sharp corner, or a patch of texture. But here is the absolute genius part and the key insight for any engineer. We don't have to sit there and design these filters by hand. The network learns them. During training, it figures out for itself which patterns are the most useful for solving the task and creates the perfect set of kernels to find them.
So as this little kernel slides or convolves across the image, it produces something we call a feature map. And it's basically a heat map. It lights up brightly wherever it found the specific pattern it was looking for. Now, because that kernel scans the entire image, it doesn't care where the feature is. And this gives CNNs their superpower, translational invariance. It can find the feature whether it's in the top left corner or the bottom right.
Now, right after the convolution, we do one more quick thing. We apply an activation function, and the most popular one by far is ReLU, which stands for Rectified Linear Unit. It does something really, really simple. It just takes any negative number in our feature map and changes it to 0. That's it. This adds nonlinearity, which is crucial for learning complex stuff. Plus, it's incredibly fast to compute, and it just makes sense, right? What would negative brightness in a picture even mean? Okay, so we've found our features. Awesome. But these feature maps can still be pretty huge and have a lot of redundant information. So the next step, the pooling layer, is all about summarizing this information to make our network faster, more efficient, and more robust. The most common method here is called max pooling. It just looks at a small window of the feature map, maybe a 2x2 square, finds the biggest number in that square, and keeps only that one, throwing the other 3 away. This makes the feature map smaller. So the obvious engineering question here is, wait a minute, aren't we just throwing away perfectly good data? And this slide just hits the nail on the head. The answer is yes, we absolutely are throwing data away, but it's a brilliant strategic sacrifice. By keeping only the strongest signal, we lose the exact location of the feature, but we gain something way more valuable, robustness. The network starts to care more that a feature is present in a general area, not its precise pixel coordinate. And as a bonus, we're shrinking our data, which means less number crunching later on and less risk of overfitting. It's a win-win. All right, so we've used our convolution and pooling layers to pull out a whole bunch of really useful features from the raw pixels. But how do we actually use all that to make a decision? To say this is a cat or this is a dog? Well, this whole process isn't a one-and-done deal. In any real CNN, we stack these blocks, convolve, ReLU, pool over and over and over. The first few layers might learn really simple things like edges and colors, but the deeper layers take the maps from those early layers and learn to combine them into more complex ideas like eyes or noses or wheels.
So what you end up with is this rich 3D stack of feature maps that represents the image at many different levels of complexity. So, to finally make a prediction, we bring back an old move, flattening. We take that big 3D stack of feature maps and, you guessed it, we unroll it into one single long vector. This step is the crucial bridge. It connects our fancy spatial feature extractor front end to a standard, fully connected neural network at the back end, which is going to do the final job of classification. So there you have it. We've built a complete basic CNN. But of course, in the real world, engineers have figured out some pretty clever ways to build on this foundation and squeeze out every last drop of performance. Let's take a quick look at some of those. A huge strategy is something called transfer learning. Basically, not reinventing the wheel. You start with a powerful pre-trained network. For example, VGG16 showed us that just going really deep with lots of simple, small filters works incredibly well. Then you have InceptionNet, which took a different route. It ran multiple filter sizes at the same time, in parallel, to catch features at different scales all at once. And then ResNet came along and changed the game with skip connections, which are like these information highways that let us train networks that are hundreds of layers deep without the signal getting lost. And finally, to make sure our model doesn't just memorize the training data, which is a huge problem called overfitting, we use regularization. We can use data augmentation to basically create fake training data by rotating, flipping, and zooming our images. We use something called batch normalization to keep the flow of data between layers clean and stable, which speeds up training. And with tools like spatial dropout, we randomly just turn off entire feature maps, which forces the network to learn multiple ways to find an object, making it way more robust in the real world. And that really brings us to the main takeaway here. The incredible power of a CNN doesn't come from any single, ridiculously complex part. It's all about the incredibly elegant way these simple building blocks, convolution, activation, pooling, are assembled into one coherent, powerful system that learns from end to end. I mean, mastering this architecture has given us everything from self-driving cars to incredible new tools for medical diagnoses. The power is just undeniable. So it really leaves us with this final thought. Now that we have the tools to build machines that can genuinely see the world, what are the most important things we should teach them to look for next? Thanks for joining this explainer.